convinced that we are dealing with atmospheric lensing. Now, I'm not exactly sure what the dictionary definition is of lensing in terms of how they're using it, but I'm thinking if the atmosphere, especially over water, is made up of zillions and zillions of tiny convex drops of water, then collectively perhaps they all combine to make one big convex lens, in which case it would act like a magnifying glass. Okay, so with that in mind, let's look up some websites dealing with the refraction of light. You might see a graphic something like this, showing light bending downward, just like the weatherman guy said. But they have sort of an unusual, although I would say very common, view as to how downward refraction is being used to allow us to see things up, over, and around the curve. And while I was looking at the Channel 57 News website, I found some raw footage, it looks like, of the conversation the weatherman had with the optics expert at that university. Check this out.
There are now lots of different ways that refraction in the atmosphere can occur. And one way that can happen is called looming. And this is a situation where cases where you can see objects in the distance that would normally be obscured by the curvature of the Earth. So as an example, in the next picture we'll show a picture taken from a person standing on the shoreline of Lake Michigan, and he can see almost to ground level Chicago, whereas normally you wouldn't be able to see that far because of the curvature of the Earth. So what's happening in this case is, especially this time of year, Lake Michigan is much colder than the air above it, and that has the effect of cooling the air just above the lake. And so now you have the case where the index of refraction is increasing with the height above the lake, and this has the effect of bending light rays back down so that they can get around the curvature of the Earth and be seen by an observer standing on the shoreline here in Michigan.
Now, prior to doing this research, I probably would have just shook my head and agreed with everything he just said, but now that I've begun to question the shape and nature of the Earth and look at it from a different perspective, this seems to me like an ad hoc theory. It seems like they start with the premise, well, we all, of course, know the Earth is a globe, it's a sphere, and Chicago's too far away for us to see it, so therefore this must be what's happening. And they create a nice graphic and take the principles that we know and understand about refraction and how the atmosphere plays into all that, and throw together again, it looks to me now like an ad hoc theory to explain how the city is thrown up over the curve so that we can see it on the other side of Lake Michigan. That's what it looks like to me anyway. All right, let's continue.
So is all this under mirage and then looming is under mirage, or what are the semantics of looming versus mirage?
Okay, well, that's all. I guess that's all in the details of the terminology. And from what I understand, technically, I think mirage has to have an inverted image, whereas there are other atmospheric effects such as looming or towering that are purely displacement, and you don't necessarily have to have an inverted image in order for refractive effects to occur in the atmosphere.
So they would all fall under the category of atmospheric refraction.
I guess that would be a good thing to say. Yes.
Okay, so again, this is their graphic. According to them, we know the Earth's a ball, so therefore this is the way it's working. Chicago's over here on the left. We got the curve of the Earth here, and the light rays, which would normally be going straight across, have to be bent due to the atmospheric lensing, the density of the atmosphere and whatnot, causing the light to refract downward, basically just conveniently enough over the top of the bulge of the curve so that we can see it on the other side. Now, here's where I would differ with this whole idea. Again, just sort of flipping the board. Let's just say we don't start with any preconceived notions of the Earth as a globe. If we start with the idea that water's flat, it always seeks its own level, and we're looking across a flat plane of water, 46 miles across. Check this image out right here. Now, I caught this image shortly after Rick and I returned from our trip across the lake. We grabbed a bite to eat, and then we went out to the beach, and it was still clear out, so we got the camera out and looked 46 miles across the lake to see this right here. This image is extraordinary. Okay, the boat right here, I'm going to guess, is less than a mile away. And I base that because these people walking in front of the camera here are walking across some rocks that sort of jut out and kind of fence in the harbor area. And they are only about a quarter of a mile away from where we were when I shot this. I shot this image from right about here. This is where we were looking across, and this is the area right here where those people were walking. And the boat, as you could tell by the size of the people on the boat, wasn't too much further beyond that. So maybe a half mile to a mile, or at the most, I would say, away from where we were. All right, now when I was headed back to Chicago to catch my flight, I snapped this picture of the Willis Tower. And this is, if you go on Google Earth, this is right about the area right here where I believe I was when I took that picture. Looking across, it's only about 0.6 of a mile. So I'm just a little over a half mile away, and look at the size of the tower as compared to the car that was diagonally in front of me. We were looking at the Willis Tower from this direction right here when we were on the other side of the lake. Now, okay, so let me slide the car over and shrink it down to the appropriate scale beside the boat. Do you see something rather interesting here? This building is significantly magnified. The image on the left shows the size and scale of the building next to a car at 0.6 of a mile away. The image on the right shows the same building and the same car with a boat at 46 miles away. The atmosphere really is acting like a lens. What type of lens? A convex lens or a magnifying glass. So I'm going to suggest this is what's happening. The atmosphere is acting like a lens, which magnifies the city, brings it up a little closer, and as it does so, we start to lose a little bit of the bottom of the buildings, and perhaps due to the density in the atmosphere, there's additional refraction that takes place that makes it drop down even more. Is that what happened? Let's look at it from another angle here, from the side view. I'll bring our graphic back in of refraction. Let's go ahead and orient the graphic so it better represents what we're looking at here. I'll angle the light rays to show the density of the air here causing the refraction, and bring our lens in so we can magnify the city. It brings the city up, and as it does so, we start to lose a little bit of the bottom of the city, and perhaps either due to the magnification or due to additional refraction, maybe it is dropped down a little bit more, and this is what we end up with. Huh. Just like we saw. Now this is a still frame from the half-hour video that I did, and the numbers you see there are all based on the numbers that Tony was giving me based on his device. His device said it was 37 nautical miles, which is 42.6 statute miles, but when you plot the same exact location that we were at, the exact distance you get on Google Earth is 46 miles. So you basically add about 4 miles to all the numbers that you saw in the half-hour video. But I'm beginning to think if that is indeed the science, and let's just go back and hear from the experts once again what's happening with the atmosphere.
The science is the same of that of a lens. Here's a simple example.
So if you're looking at Chicago here, just maybe now you can just see the top of the Sears Tower, and if our simulated temperature inversion moves into place, hopefully now you can see pretty much all of Chicago,
see all the lower buildings,
including what's at ground level.
So the atmosphere really is acting like a lens.
Yes.
So the atmosphere really is acting like a lens, according to the experts. Now, you guys don't need to go out and spend tens of thousands of dollars to get that pretty piece of paper to hang up on the I Love Me wall and put letters after your name so that you can call yourself an expert. You can be an expert with what you see here on the screen. Yep, believe it or not. Go to Walmart, And your advanced degree in atmospheric lensing technology will cost you just a couple dollars. You can get a 2x power lens for about $1.85, I think, at Walmart. Get yourself some Scotch tape. Then if you look in the description below, you'll see I put a PNG file of a city. You can print that up, cut it out so it looks something like this, what you see on the screen here. Then find a table and a chair. And okay, you're going to bend the paper so it looks something like this. Tape the lens to the table, get a chair that's about the same height as the edge of the table. Put your iPhone on the end of the chair, and the chair will act as a dolly, so you can just kind of pull the chair back. And looky here. Look what happens with atmospheric lensing. Wow, isn't that amazing? And you didn't have to go to college either. Now, you can get in a boat and drive to Chicago, and wow, look at that. Now, let's compare. See? Look at this. This is how much of the city was lost simply due to atmospheric lensing. Now remember, the experts, the guys that spent tens of thousands of dollars to get advanced degrees in this stuff so that people would recognize that they're smart, they told you the science really is that of a lens. Now, of course, the first time I posted something like this on YouTube, the baltards came out from under every rock on this plane to make fun of me and say I didn't know what I was talking about with refraction. That's not how it works, and blah, blah, blah. And they looked at the image on the lower right here of the magnifying glass showing the city and how it was all wavy and distorted. And they said, well, look, your magnifying glass made everything distorted, and Joshua Nowicki's picture was straight up and down. You're an idiot, blah, blah, blah. Well, yeah, okay, so then these other guys came out and they started posting all this stuff about the Toronto skyline. And you've probably seen the meme being passed around on Facebook and everything, showing the lower portion of one of the tall buildings there in Toronto being missing, and they're saying, see, this is proof of the globe. And you start seeing videos like this one.
Another way to demonstrate the curve is with distant city skylines. A good example is the city of Toronto, viewed from across Lake Ontario. The city is dominated by the distinctive CN Tower, currently the third tallest tower in the world at 1,815 feet. There are many pictures online of the Toronto skyline, viewed from Niagara-on-the-Lake, New York, 30 miles away. With the metabunk calculation, we see that 486 feet of the tower, or about 26% of it, should be hidden behind the curve of the Earth from that distance. And this is exactly what we see, as you can easily tell when compared to an image of the full tower at the same scale. One example they use is the Chicago skyline seen from 60 miles away across Lake Michigan. At a viewing height of 6 feet, we calculate that 2,166 feet should be below the horizon at 60 miles. So they are right that the entire city of Chicago should be completely hidden. And it is hidden nearly all the time, but sometimes it can be seen from that far away due to a type of atmospheric light refraction phenomenon called a superior mirage. A superior mirage is caused by colder air below warmer air, which bends the light around the curve of the Earth. This event sometimes makes the news for the very reason that it is a rare occurrence.
Now, in most social settings, such a continuous condescending tone would likely get you punched in the face repeatedly, but beyond that, I have to remind you of the response that another former weatherman gave regarding the whole idea of this being a superior mirage. Let me play that for you again.
See, what they're not showing you is the ridiculousness of how high this mirage would be. But I'm showing you what it is right here. And remember, since we saw the water line the whole way, okay, let me show you how that would look. The water was up there with it too. So from the guy that took the camera all the way out, okay, we're supposed to believe that there was a continuous 5,200 feet inversion that suddenly just happened to come down to the guy right on the edge perfectly, so that he saw, when he looked out, like a perfect skyline across there of Chicago. So again, here are the steps. You have the regular right side up image, then you turn it upside down. It has to happen on a mirage, guys. This is the typical one you see out at sea, this upside down one right here. Now what they're claiming is it was so deep, this layer here, this inversion, that it had enough to rectify back up once again. 5,200 feet. Now why did I come up with that number? Because the curvature from the distance would be 2,400 feet roughly from 60 miles. So if it happened to get the exact perfect curvature from the top of these towers, okay, it would require a minimum. Actually, it requires more than this. I'm being generous. It requires 2,400 feet plus the height of the tower. It would be 2,400 feet just to get the base. So I'm not even including that. What's the height of the tower? I don't know, whatever that is. So many, is it 1,000 feet, 1,200 feet, 14? I don't know what it is. But that's really that times 3, not 2,400. I'm being very generous. So if we were to, you've probably seen, look up superior mirages. You'll find like ships that will be upside down looking, one on top of the other. That's the typical superior mirage, which you would see right here. Okay? That would be a minimum of 4,800 feet. But since the image was not inverted and right side up, which really tells you you're looking at Chicago, you're not looking at a superior mirage. Okay? It requires 5,200 feet. I implore you, please call any National Weather Service office and ask them if they've ever seen an inversion from the surface up to 5,200 feet. Okay? They're going to laugh at you.
Now let's go back to Captain Baltard.
You can tell that it's a mirage because there is lots of distortion. The Willis Tower on the left is clearly elongated. And also, there are videos of this same view that show the buildings dancing around, changing shape, and even disappearing. Even though this is a mirage, the bottom parts of the buildings are clearly still obscured from view, just as we expect. If the Earth was flat, you could see the buildings on any clear day, not just rarely when the conditions are right for refraction. Flat earthers use these rare events to try to prove the Earth is flat, but that makes no sense. It's called cherry picking, a favorite trick of all types of science deniers. You don't get to pick the anomalies that seem to agree with your views and ignore the common observations that don't, and still call yourself an honest investigator. That is intellectually dishonest.
Now let's see who's going to pick and choose what common observations they're going to accept and or ignore. Here's an interesting video I saw online regarding a full day time lapse revealing superior mirages. Now this is quite extraordinary actually. This is from skunkbayweather.com, September 7th, 2012. Notice the buildings and the shoreline here over on the left. Keep your eye on that. Just watch that, and the mountain in the background. Yeah, everything's pretty cool. You can see pretty much everything there, but as the day progresses, and we are now at 9:30 a.m. and it's 59 degrees, 60 degrees, it's getting warmer, the temperature is changing, we start to see some miraging take place, right? It starts to distort things a little bit. Ooh, look at that. The water seems like it's getting higher, and we're losing buildings, and we're losing the beach. Here it is now, noon, 63 degrees and climbing. Uh-oh, there it goes. Oh, there it is again. Oh, it's all miraged. Huh, it's all distorted. Sometimes you see it, sometimes you don't. The default is to see it, though. That's the point. The default is minus distorting atmospheric conditions, you would be able to see everything clearly. But due to different temperature variations and density in the atmosphere and whatnot, sometimes you can see the whole shoreline and the buildings, sometimes you can't. But the magic trick is not in being able to see it. It's what is taking place that obscures your ability to do so. Look at this. And the mountains in the background shrink and expand and everything too. I would suggest that you hit pause on this video and rewind and watch that back and forth a few times. In fact, I'll put the link in the show notes below because I sped this up. I made it only 2 minutes long instead of 4 minutes long. So you can watch the whole thing in a little bit slower motion there, but I mean, look at the comparison right here, just in these two images right here. The one on the right at 5:44 p.m., 63.5 degrees Fahrenheit, can't really see anything on the left shoreline there. And on the left at 9:43 a.m., when it was 59.5 degrees Fahrenheit, we can see the shoreline, we can see buildings, trees, all kinds of stuff. So, I mean, either this lake is, filling up and draining so that the water level is higher or lower, or it's due to atmospheric lensing and distortions, refraction, and all that good stuff, causing us to not be able to see it at certain times. I think that's exactly what's going on Lake Michigan. And again, based on that imagery that I saw looking 46 miles across versus 0.6 miles across, I really do believe that, just like the experts said, the globalist guys, these are people who believe in the globe now, they are the ones that said, hey, the atmosphere really is acting like a lens, and they put a lens in front of the camera to show how it works. So I'm just doing what they're doing. I'm using the same logic that they're using, the same science that they're using. And, science is all about testable, observable, and repeatable data, right? So, to alleviate the problem of distorting the edges because the magnifying glass ring is too small, I went on Amazon and I got these plastic magnifying sheets and came up with another way of doing the same thing using the sheet right here. Set the city up, a little cutout of the city, and now I've got the big magnifying glass sheet. Bring the camera right up to the lens. See, that's the normal view of the city. Now let's back up again.
The science is the same of that of a lens. Here's a simple example.
So if you're looking at Chicago here,
The atmosphere really is acting like a lens.
yes.
Atmosphere really is acting like a lens, and this is how much of the city is missing due to the lensing effect, the magnification of the atmosphere. You're missing a good portion of the city just by pulling my iPhone back on a 3-foot long desk. That's how much I lost of the city. And as with any scientific experiment, you always try to improve upon what you did before. So I got some foam core, made a little housing for the magnifying sheet, and pasted the city on the back there, and I made it as two separate pieces so that I could flex it as necessary, because I think that there are different types of atmospheric conditions that would allow for more magnification versus less magnification. So in this scenario you have more magnification, and in this one you have less. And for this one I decided to put the Toronto skyline into my little box here. And let's try it again. Okay, we're all the way up against the glass. Now let's zoom across the lake. And wow, look at that. The lower portions start to disappear. Now let's zoom back in to get a little closer to the one that Captain Baltard was talking about here. And wow, look at this. Here's his image on the right, and here's my image on the left. Missing the lower portions of the city had nothing to do with curvature whatsoever. Thanks so much for watching. I hope you enjoyed this video presentation. If you did, please subscribe to my YouTube channel, like the video, and share it on your favorite social media sites. There's a lot more to come, so stay tuned and we'll see you back next time.